Hello and welcome back to the course on blockchain. And today we've got another exciting tutorial ahead. We're talking about how miners pick their transactions. Alright, let's get straight into it. Okay, so here we've got a miner. As usual, we're just used to illustrating miners with laptops now, so this is going to be our miner. And so how does a miner get the list of transactions that actually goes into this field? All right, so we kind of know the rest, and we've been using the transaction, those fake transactions that I made up with the altcoins. But in reality, where do these transactions come from? All right, so that's what we're going to be sorting out today. Well, the transactions, they come from something called a mempool or a memory pool, which is attached to every node, every miner. And basically, these are all the unconfirmed transactions that they get stored here before they get included inside a block. So blocks are added about every 10 minutes, but transactions happen all the time. So, I can send some Bitcoins now, I can receive some Bitcoins. We don't have to wait until every 10 minutes to do that. We can do that all the time. So all those transactions get put into a mempool in the meantime. It's like a staging area for transactions. We'll talk more about the mempool in an upcoming tutorial further down the track. We'll understand how it works exactly in more detail. But for now, that's sufficient information for us. That a miner or every node has a mempool attached to them where there's a list of transactions that are still pending, like a staging area. And so the miner will need to include some of these transactions in the block. And let's say the miner has a maximum for argument's sake, that there's a maximum of 5 transactions that they can include. In the real blockchain world, there's a different limit. The limit is 1 megabyte, and then however transactions fit in there, and that's about 2,000 transactions fit per block. But for our purposes, we'll just say that a miner can include maximum 5 transactions here. Okay, so how is the miner going to pick these transactions? Well, if we look at them, we can see like there's a transaction ID, which is much longer in real life. And then there's some more information usually, but here you can see that there's the fees that the miner will get for including each one of these transactions. And fees, again, that's another topic we'll cover further down the course. But for now, we just need to know that fees are non-compulsory and they're specified by the users themselves. So whoever sends the Bitcoins, like if, for instance, I send Hadelin some Bitcoins, I can say, I'm going to send him this amount, but this is the fee I'm going to pay. And then it's absolutely arbitrary, absolutely up to you. You can put a 0 fee, you can put a high fee, you can put any type of fee. But the miners, they actually get these fees. So if the miner is successful in creating this block, then he's going to get the fees that are attached to this block. So he's obviously going to pick the highest fees. So this one, as you can see, it's the highest out of all of them. Then this one, and this one. So there we go. Those are the 5 transactions with the highest fees. That's the first choice of the miner. Like all other things equal, which they are, why would the miner choose anything else if he can only choose 5 transactions? So he's going to put them inside the block. Okay, and so that's how where these transactions come from. And now, as promised previously, we're going to return to our nonce problem, our nonce challenge, which or issue which we identified in the previous tutorial. Let's have a quick reminder of what that challenge was. So we established that the nonce is a number between 0 and 4 billion. It's an integer. And that's the range where we can pick the nonce from. And so we have a timestamp. We identified in the previous tutorial that we also have a timestamp in our block. And so now, now we're going to set off the timer. And if in 1 second the miner doesn't get to the end of the nonce, then everything is great. Everything is totally fine because he's gone through a lot of different numbers, a lot of different integers. They've all generated their own hashes. And he's checked them, probably he's most likely not found a valid hash that would make this block valid. So he hasn't found a golden nonce. And therefore, 1 second has passed. What happens next is the timestamp gets updated by 1 second and he can go through these nonces again. right? So let's see how he does that. He goes again, bam, another second, and again. So basically, that's the reusability of the nonce because of the timestamp, simply because the miner is not fast enough to go through 4 billion nonces within 1 second. And that's a good setup if you're one miner. But if you're a pool of miners, or if you're a miner who's got a lot of processing power that you can go through so much more than 4 billion hashes in 1 second, right? So as we saw previously, the total hashing rate, total hash rate of the network combined right now is 22 million trillion hashes per second. Million trillion, you know, and this is only 4 billion. So they're definitely going to go through. And, you know, obviously that's the whole network. So a pool that says, let's say, has 10% of the network would be 2 million trillion. Still, that is way more than 4 billion. And so they would go through the nonce like nothing, like very quickly, in no time. And so the challenge or the issue that we identified, what architecture in the network allows such big players to not have idle capacity, right? Because if they go through the nonce, right? So let's have a look at an example, right? So let's say they're extremely fast and bam, they went through the nonce, this whole thing, in less than a second, like that, right? So what do they do now? They still have, I don't know how much, like more than half a second left of time, or like 0.7 or 0.6 of a second, 0.6 of a second left. What are they going to do with this idle capacity? Do they really have to wait until this number updates? Because there's no point of them going through the nonce again. If they go through the nonce again, what happens is, as we remember, because nothing else has changed in this block, because of that, we know that the SHA-256 hash, or for that matter any hash, has this cryptographic property that it is deterministic. That you put in, and if you have the same inputs, you will always get the same outputs, and there's no point in going through the nonce again. Well, the solution or the architectural design from this slide, that begs the question: what can we do? What is the architectural inbuilt solution in the protocol of Bitcoin that allows to overcome the challenge? And for even miners with a lot of hashing power to participate, or mining pools to work properly. So the solution from this slide, we kind of started with the solution. So the solution is to change the block configuration. Because remember, at the very start of this tutorial, we were picking the transactions based on the highest fees. So we put the transactions in here. The miner gets to choose the transactions they put, and they put the highest fees. But if you put the transactions with the highest fees and you went through the whole nonce in less than a second, and you haven't found the hash yet, the valid hash, then what else have you got to do but to change the configuration of the block? And that's exactly what a miner will do. So let's have a look at that. So the miner will say, let's look at the transaction with the lowest fee. Out of the ones I've picked, which is the one that has the lowest fee? It's this one. It's only 0.0004, less than all other transactions in the ones I've picked. So I'm going to take it out of my choice. I'm going to remove it. And now I'm going to pick the next transaction with the next highest fee, which is this one. And I'm going to put it into my block configuration. There we go. And so now, because the block configuration has changed, the data inside the block has changed. You'll notice that the timestamp hasn't changed, but the data has changed inside the block. And so so that means that we can now reuse the hash, reuse the nonce, and for every single nonce number, overall this will be different, and therefore it'll have a different hash, right? So there we go. Now we can just launch this whole thing again. Bam. As we can see, the miner again went through the whole nonce, and again the whole time here, we're looking at the total time, is less than a second. And again, he still hasn't found the hash. So what happens now? Same thing, change block configuration. All right, let's identify transaction with the lowest fees. It's this one, which we just included, like throw it away, and find the one with the next highest fees. Okay, this one. All right, good, put it into the block. Wonderful. and now the miner goes off again. Bam. And as you can see, now we've reached 1 second. All of that, we've been talking for like 5 minutes, and all of that was actually 1 second in the world of mining. And the miner hasn't finished this nonce, wasn't able to even finish this nonce. Again, hasn't found the hash. But now what happens? Finally, a relief. The timestamp gets updated to now it's a new second, and that means everything here has changed. And that means we can start all over again. And what does that mean? It means the timer gets reset, nonce can get start from 0, and as well, let's not forget, we can now get rid of this transaction with this fee and put in that high fee transaction again back in. Okay, and there we go. There's our new transaction back in the block. And there we go. So basically, now we're starting the whole thing afresh. So that's how miners pick transactions, and that's how mining pools or large miners, that's just any miner, so algorithmically solves the problem. So the important notes here is, number one, is all of this happens algorithmically. All of this, the miner doesn't sit there and pick out transactions. That would be impossible because you only have 1 second for that to happen, and you're doing like the pool is doing like 2 million trillion transactions per second. So all of this is encoded in the algorithms that govern how people are mining, and that's part of the service. So now, like, let's say if it's an independent miner that is not part of a pool, then for some reason doing that, or like somebody with a very powerful computer, then they need to come up with that algorithm. If you join a pool, then that's part of the service that the pool provides. So when you redirect your hashing power into a pool, you don't need to think about this. Remember, this is one of the things we talked about, the advantages of a pool, that they get rid of the headache. The miners they take away the headache from the miners. So if you redirect your hashing power to a mining pool, they will allocate you the right transactions that you need to be working on. And so a pool knows that they have a couple, 1,000, 10,000, 100,000 miners in there, and they know that, okay, the algorithm already knows how to allocate the transactions. And remember, there's not only like whatever we have here, 11 transactions in the whole mempool. There's usually like 7,000 transactions. So they know the algorithm automatically combines the transactions in the best possible way in order to maximize the fees, but also in order for the miners not to duplicate their work, for different miners in the pool not to duplicate their work. It's a very smart algorithm. And so it allocates the work to the miners, it allocates the transaction fees, allocates the nonces, and so on. And the miners then just like they churn away and churn away and churn away, and eventually somebody finds that golden nonce or finds a valid hash. And so that's point number 2. And point number 3 is, as you can see from here, and this is something we'll be talking about further in the course, if you specify a very low fee in your transaction, like a 0 something, it is likely to get stuck in the mempool. Like no miner will ever use it. Maybe by accident sometime, not accident, like through this process of distribution by the algorithm, it might use your transaction, might need to like switch over, but because it has such a variety, it has like 7,000 transactions to choose from, they usually start like, from the highest fees. They have like a threshold. They don't even look at transactions below a certain threshold for their allocation. And then what happens is your transaction will be released back to you. I think the new standard right now is within 72 hours. If it's not picked up by any miner, then it'll be released back to you. So it's also like your wallet will usually help you identify what the current fees, average fees are, and what you need to input in order for your transaction not to get stuck in the mempool. So that's just another thing to know. Okay, so that's how this miners pick transactions, and now we know there's actually a couple of things that change in the block. So the timestamp changes, the nonce is something we can control, and the actual fees. Finally, we've uncovered how we can control, not the fees, the transactions, how we can control the transactions inside the block in order to all of these things influence the hash. Okay, and so that's that. Let's have a look at some charts again.